you are very welcome to the seminar this morning. And today we are very honored to have a distinguished scientist from Columbia University, Professor Sobel, to visit us. So let's give us a warm welcome to Professor Sobel. Because Professor Wu from National Taiwan University is more familiar with Professor Sobel, so I will ask Professor Wu to give us a brief introduction of Professor Sobel. So let's welcome Professor Wu.
谢谢，不好意思，简单 OK. So let me briefly introduce Professor Adam Sobel, and he's visiting Taiwan for 1 week, and this is the fourth day of his visit. And Professor Sobel, he is a very interesting guy. He has a background for his undergraduate in music and physics, both double majors. So he was kind of playing music all the time since he was a young man. And at the college, he went on actually, he was most of the time maybe working with music for sometimes 2 years. And then he decided I think he feel that he likes science better, so he got back and he went to school in MIT for his PhD with Professor Alan Klein. At that time, working on the vortex and polar vortex and stratospheric dynamics. And after his PhD in 1997, he went to work with Chris Redman at the University of Washington for 2 years on tropical dynamics. So he changed his field completely after postdocs. And then he got his faculty position at Columbia University starting from 1999. And he was tenured just 1 year ago at Columbia University. So he's taking his sabbatical leave right now at Melbourne, BMRC in Australia. That's why he's applying. So he got so close to Taiwan now, much closer than US. So he got a chance to come over to visit us here. And he will also go to Japan for another meeting next week. And if you look at all his website, you'll be amazed on how many works and publications he already had for the past few years. You can go and check. And his main interest right now is about tropical dynamics from theoretical, modeling, and also observational perspectives. So very broad. So he's a very smart and sharp guy. So I think we'll enjoy his talk today. Okay, so let's welcome him again.
Thank you very much, Professor Wu, for the very generous introduction and for inviting me here to Taiwan. And thanks to people here at NCU for hosting me today. It's a great pleasure to speak with you. I hope I can live up to the introduction. The title here is slightly different than what I sent, but the talk is the same. I just forgot what title I sent, but I made up a different title. It doesn't matter. Professor Wu likes this title better, so I kept this one. So, yeah, I want to talk about sort of 2 different pieces of work today that are recently published in 2 different papers, but the idea behind them is really the same. 2 different ways of using the same idea and trying to understand. The basic idea is we're all interested in how the tropical cyclones change over time with climate change, and we want to use interannual variability as a test of our theories and our ideas for how that works. So we all know that if the environment changes, climate warms, or the circulation changes, the cyclones may change, and we have some ideas what are the mechanisms for that. But those ideas are incomplete, and we're not sure how good they are. So we use interannual variability as a kind of lab to test those ideas. Okay. So I will say more as time goes. This work is all recently published in these papers. If you are interested, you don't have to write it down. I will show the webpage later. But it's done with several colleagues I want to acknowledge. A lot of this work is really done by my colleague Susanna Camargo at Lamont Doherty Earth Observatory, which is part of Columbia University. She's the first author on 2 of these papers, and she really did most of the work. This one paper, a lot of the work was done by Alison Wing at Cornell, a very, very smart undergraduate, 19 years old when she did this work, and just in the summer. And then we finished it after she left. Some of this work is joined with Kerry Emanuel at MIT, and actually all of it is using his ideas. All of this work is extending ideas of Emanuel. So he is playing a big role even when he didn't help us with the work. We're still using his ideas. And one of the papers is joined with a guy named Tony Barnston at IRI, which I think some of you know, people from IRI. Maybe even met Barnston here in Taiwan at some point. So the big questions that many of us, including I'm sure many people in this room, are interested in is what controls the statistics of tropical cyclones. So by statistics we mean not just the individuals forecasting individual storms, but understanding what will happen in a whole season or a whole decade. Will this year be more active than last year, or will 30 years from now we have more cyclones than now, or less, or what? So we're interested in the numbers, how many storms we will have as the climate varies. And we could be talking about natural variability, anthropogenic. At this point, we want to know the mechanisms. We don't care why the climate changes. We want to know how the climate change is related to, or climate variability is related to cyclones. So there's two aspects, the numbers and the intensities that we are interested in. What controls that? And then, of course, there's a lot of debate now how all these statistics change as the climate changes, say due to anthropogenic global warming. So the theme in this talk today is we're going to use interannual variability of the cyclone statistics, which is mostly natural, mostly due to El Nino and other phenomena, but El Nino is a dominant one. El Nino, La Nina, and so. And we look at the historical record where we have, maybe 30 or 50 years worth of data in the tropical cyclone database, and we compare the variability of the cyclone statistics, the numbers and intensities, to the interannual variability of the environment. But the environment is measured by some indices which come from theory or empiricism or some combination that tell us how genesis or intensification are related to the environment. So for the intensity, we have potential intensity theory due to mostly Kerry Emanuel, Greg Holland, and a few others who came before and after them. Potential intensity theory is really the main theoretical basis we have for understanding intensity. So we will use interannual variability to see if what potential intensity theory tells us about how climate and cyclones should be related is true, if used at least as sampled by interannual variability. And then for the genesis, we don't really have a theory, but we have some empirical indices. The first one is by Gray, and later other people, including Emanuel, have made new ones, but the idea is original to Gray, I believe. And these indices are partly theoretical in that we have some ideas physically what are the important factors on genesis, shear, relative humidity, sea surface temperature, all these things. But then how these indices determine genesis, we don't really have a theory. We have just these empirical indices which come from looking at the observations. But we can use the interannual variability. Those indices are built to capture the climatology. But we can use the interannual variability to test how well they work under climate variability. And if they work well, then we can use them to, in some slightly more sophisticated ways, we can take apart those indices to see which environmental variables are most important in controlling variability. And I will elaborate more on that as time goes on. So I really am going to talk about two pieces of work. One using interannual variability to test potential intensity theory, and one using it to test an empirically derived genesis index. And I will talk about those both in turn. So let's talk about potential intensity theory first. I'm not going to give a whole review of potential intensity theory because it would take the whole hour, and it's old work anyway, not due to me. These are some references, but I think really Kerry Emanuel deserves most of the credit for developing this idea. But I will give a few things about it. But if you don't know what potential intensity theory is, then maybe you can ask a question at the end if I can give more detail. But for now, what matters is the potential intensity is a theoretical upper bound to cyclone intensity. So if you know the environment, the large-scale environment, the sea surface temperature, the atmospheric profile of temperature and humidity on the large scale, then Emanuel and Holland developed two different theoretical frameworks that give somewhat different but mostly similar answers about what the maximum intensity a cyclone can reach given those environmental factors. In Emmanuel's case, this is based on thermodynamic efficiency of a Carnot heat engine. So it's based on a physical theory. Okay, it's a theoretical upper bound. And most storms do not reach the potential intensity, but it's the maximum possible. They can get anything up to that. That's what the theory says. And this shows from Emmanuel's early paper. This is a plot of the potential intensity in the climatology. The units are millibars. So it's the minimum central pressure that's possible theoretically. You see, of course, the most intense possible storms right near Taiwan, as you all know, are living here. And these pluses here are the values of the most intense storms ever observed at those locations. So you see the match is quite good. This says the minimum central pressure is 880 and the most intense storms are pretty close to 880. And similarly here, another 880 in these most intense storms here. So this is really, to me, a great success of atmospheric science, even though now there are some questions about whether the assumptions of potential intensity theory are really exactly correct. But nonetheless, it's an analytical theory that gives a very remarkably accurate prediction for the maximum intensity of observed cyclones. So we're not going to go into the details of how the theory works, but it's a theory that gives us an upper bound on the intensity. Okay, that's what we need to know for now. In this study, there's a few different ones. There's the Emmanuel PI and the Holland one, which is different. We're going to use the Emmanuel one, and this is the formula. I don't want to say too much about it, but I might as well show what it is. This is the maximum intensity as the maximum wind speed squared, is what the theory predicts, and it says it's a function of these two temperatures, a surface temperature and an outflow temperature, a temperature at the top of the cyclone outflow. CK and CD are the exchange coefficients for enthalpy and momentum, so the bulk exchange coefficients at the surface. Theta E star and theta E are the saturated equivalent potential temperature and the equivalent potential temperature at the surface at the radius of maximum wind. And you don't know exactly what the radius of maximum wind is, so to compute this thing is actually a little more complicated than it seems here. But because you have to do some nonlinear iteration to actually compute these numbers. But anyway, we have an algorithm to compute this. This is wrong. So this didn't come out right. This should be theta E star. Anyway, through some algebra, you can convert this formula to this one. They're equivalent, where CAPE is convective available potential energy, and this is the saturation one, and this is the real CAPE. And we use this one for various reasons to compute the potential intensity. It's Emmanuel's algorithm. And so, without going into details, the potential intensity, when we actually compute it from data, it depends on the sea surface temperature and also the whole profile of atmospheric temperature, because to compute CAPE, you need the atmospheric temperature. So we use enthalpy analysis for that. Okay, that's about all I'm going to say about what the PI is. But now, okay, the potential intensity is just the maximum possible intensity. So if you want to know what's the actual intensity going to be, the potential intensity theory doesn't tell you that. Since most storms do not get that strong, you have to make some other assumption. And if you want to predict the interannual variability or the long-term trend in climate in cyclones based on a projection of the change in the environment, you need to know the real intensity, not the potential intensity. So there we don't really have a theory, but we have an empirical result, this time also due to Emmanuel. And what he did here was take the statistics from two basins, the North Atlantic and Western North Pacific, and take all the storms ever observed, and for each storm, normalize the actual intensity, the maximum intensity, by the potential intensity along the track. So that gives you a number usually between 0 and 1, but sometimes the real intensity exceeds the potential intensity, and it doesn't actually show that the theory is wrong, because sometimes a storm can become very intense and then quickly move to a place where the water is colder. So then it takes a while to adjust to the new conditions, and during that time it overshoots, the potential intensity drops faster than the real intensity adjusts. So he has to be a little careful about how to treat those cases, and in this case he takes those out, the storms where they cross quickly over cold water. Or sometimes you can just use the maximum intensity that happens before you reach the cold water. There's a few different subtle ways of doing that. But the main point is, takes all the storms, finds a normalized potential intensity, which is a number between a normalized intensity. Intensity divided by potential should be a number between 0 and 1. Okay? So you have a whole database, many numbers between 0 and 1, and from that you can compute statistics of that whole distribution. So this is the cumulative distribution function of those storms from the observed database. So this is numbers between 0 and 1 here, and this is the frequency. Now this is a cumulative distribution function, not the PDF, but the CDF. So it has to decrease. So this tells you what fraction of the storms reach, say here, this number here, 10, is what fraction of the storms in some arbitrary units reach 50% of their potential intensity. That's this value here, or less. Okay? That's this curve. And now, these two curves are, this one is separately plotting storms which reach at least hurricane intensity and those which only reach tropical storm intensity. And you get two different curves, but both lines. And this is where he throws out the cases of where they cross into rapidly declining potential intensity or cold water. This is all the storms together, but only taking the maximum intensity reached before the crossing of cold water. So you don't need to worry too much about the details. The main point is this is a line. Okay? Cumulative distribution function is a line. Now the PDF, the probability density function, will be the derivative of this. So that's a constant. So that implies that the theory says that, not the theory, this empirical result, it's an empirical result, there's no explanation of this, it just comes from the data. And it says that any storm is equally likely to reach any intensity between some lower bound, which we don't know what it is, and its potential intensity. So it could reach 0.4 times the PI or 0.6 is equally likely. Okay? That's kind of interesting result. And what it says, if you assume that will stay the same always, that distribution function is some kind of universal thing, some feature of the climate, we don't know why, but assuming that it will always be like that, it gives you a prediction of how the actual intensity will change when climate changes. Because if the climate changes, you compute the new potential intensity, and you know the real intensities will be some uniform distribution up to that. So then you have a prediction of the statistics. Okay? Up to sampling error, because there's usually not that many storms in a given year. So the prediction is, and what Emmanuel wrote in his paper, is that a given percentage increase in potential intensity leads to an equal percentage increase in actual intensity. So if PI increases 10%, the real intensities will also increase 10%. Okay? Now that's true if you don't put a fixed threshold on the data. If you put a fixed threshold on the data, like say you only consider storms which reach hurricane intensity. Hurricane intensity is a fixed number, so without going into the details of it, the prediction ends up being slightly different. You have to compare the data to the theory in the right way, and when you do that, the predicted percentage increase in intensity will be a little bit less than the increase in PI. And I'll give you the actual formula. It's straightforward statistics to show that, but I won't go into the details. So we call this PI theory, even though it's not just PI theory, it's PI theory plus the empirical result of uniform distribution. That's when I say PI theory, I mean that whole thing. Change in PI gives us a change in intensity by assuming uniform distribution. That's what we're going to test that on the interannual variability. When we have ENSO, the PI will change. So do the actual storms change in the same way as PI theory predicts? And the thing we like about looking at interannual variability is that it doesn't have the same biases as the trends. When you look at the trends in potential intensity, people argue a lot because the best track database, which is all we have really, the observing system changes over time. People use the Dvorak technique, and different people use it different ways at different times. The operational agencies change their ways of recording the storms. So when you look at the long-term trends, there are biases which make it hard. But the interannual variability doesn't have that because the observing practices don't change with ENSO. So that there is a small projection onto the ENSO, but by and large it's independent. So that's what we like about looking at interannual variability. It's a more clean test of the theory than the trends. Okay, so what we do, I'm taking more time than I meant to, so I want to go kind of quickly, but you should understand what we did. So we use the best track data to define the track of storms and the intensity of storms. So the V here is the maximum wind recorded in the best track data set. And we, again, look at the North Atlantic and Western North Pacific basins because those have the best data. We compute the potential intensity using the Interannual formula, which I showed before, using the CAPE. And we compute it along the track of the actual storm. And we use the monthly mean reanalysis data to compute the PI. So there could be some error there because the actual environment may change a little faster than monthly, but we accept that error. Don't worry about it. It's the same thing Emmanuel did actually in his study. He also used monthly mean. We find the point each storm reached the maximum intensity, and at that point we save the actual intensity and the potential intensity at that point. Okay? And in some calculations we throw the storms away if V over P exceeds 1. And sometimes, which is about 20, so V over P is the real intensity divided by the PI. That violates the theory, so sometimes we throw them away. It's about 20% of the storm. Sometimes we keep them. And I'm not going to be that explicit about when we do it. If you're interested in that subtlety, I can ask a question. But for the analysis here, it doesn't matter too much exactly how we do that. Then we average together each year, so we have some set of points. Each storm gives us one number between 0 and 1. Or in some cases can be a little bit greater than 1. Each year, we average those numbers together. So we get an average storm intensity, normalized storm intensity for that year. We also have an average PI for that year, and then we compare those two time series. Okay? And we make a scatter plot of all those points in the time series, and PI theory tells us what the slope of that scatter plot should be, the regression slope, and also tells us, and also it doesn't tell us what the correlation should be, but if PI theory would be useful, it should have at least some significant correlation. Otherwise, it doesn't explain any variance, then we don't care, right? So if you work out the and we first detrend the data, so we're just looking at the interannual variability or decadal variability, but not the long-term trend, okay? And without going into the math, it's very simple to show that the PI theory predicts that the regression slope should be the potential intensity divided by the potential intensity plus the minimum threshold you apply to the data, which might be hurricane intensity or might be nothing. So if you don't apply any threshold, the predicted slope is 1 for the normalized regression slope. But if you put some other threshold, it will be less than 1. Okay? And what the value is depends a little bit on the data because it depends what P is. Okay, I already said all that. So this is the time series. So this one with the pluses is the time series of the actual intensities for each year. This one, the solid curve without the plus, is potential intensity for each year on the tracks at the point of maximum intensity. And this dot dash curve is the potential intensity for each year averaged over the main development region of the Atlantic. Okay, so fixed region. So this one is computed on the track, so what that place is different every year. But this one is just averaged over a whole area that never moves. Okay, and the same thing for the Pacific, where we define some main development region for the Pacific. I don't remember the exact latitude and longitude, but it's the region of the most storms forming. So what you see, first of all, there is some correlation between the real intensity and the potential intensity. Usually the curves don't cross. The PI is higher than the real intensity, which should be. But once in a while they do cross because it's possible. In this calculation, I didn't throw away the points. Yes?
How does the real intensity be determined?
Best track. Best track data set.
So does the value calculated from the analysis data?
The actual intensity comes from best track, but the potential intensity comes from the reanalysis. But I compute it at the point where the storm is according to the best track location. So right, the potential intensity is a two-dimensional field that I compute from the reanalysis, and then the storm has a track, and I look at the best track and see when does that storm reach maximum intensity. Okay? At that time, in that place, I compute the potential intensity from the reanalysis. But it's a monthly mean reanalysis, so it doesn't know about the storm really.
So the potential intensity is still based on the reanalysis data.
The potential intensity is, the actual intensity is not. So those data sets are independent. Yeah. Great. Thank you. So these are correlated. PI is usually greater than actual intensity, which should be. the potential intensity in the main development region is usually larger than that in the storm. So the storms are, on average, experiencing a lower PI than the MDR. Some of them form in the MDR, but some of them form somewhere else. The other interesting result is that the MDI, the potential intensity of the MDR varies much less than the PI on the tracks. So it tells you something interesting right away, which is that the storms on the fact that the PI on the tracks is fluctuating so much is not because the MDR potential intensity is fluctuating so much. It's because the tracks are moving to some place where the potential intensity is different from year to year. So the potential intensity fluctuations experienced by the storms are not due to the change in the potential intensity field so much. They're due to the storms sampling the potential intensity field in a different way by the tracks shifting. Okay, that's kind of an interesting result we have to keep in mind when we want to think about how to compare this theory. You can't just take the MDR and use that. Okay. All right, so that's that. Now let's do the statistics. This is just taking these two time series, the plus and the solid, and make a scatter plot of those points. Okay? So PI theory tells us what the slope should be. This is for the Atlantic, this is for the Pacific. The correlation in the Atlantic is 0.5, so it explains about 25% of the variance. Not that much, but it's significant. Okay? The slope from the regression is 0.49. This is shown here, the regression, linear regression slope. The theory is 0.65. It seems different, but if you look, the difference is not very much. And if you compute 95% confidence limits, this slope is well within the confidence limits of this. So it agrees within the noise in the data. It agrees with the theory. The noise is large, but there's 75% of the variance we don't explain. But within that error, it agrees. And same is true in the Pacific. Actually, the slopes are extremely close to the theory, which I think is just 1. But there's also still the error bar is quite large, and we only explain only about 20% of the variance there. But both of these are significant correlations, and the slope does agree with the theory. This is a summary of the statistics. This is Atlantic and the Pacific. Where it says tracks, it means the PI is computed on the tracks. Where it says MDR, it means it's computed in the MDR. This one includes tropical storms. If it doesn't say TS, it does not include tropical storms. It's only hurricane intensity or higher. And you think PI theory should apply better for more intense storms. If its storm is tropical storm and then shear kills it or something, it never gets close to the PI. Maybe PI theory should work. But anyway, we computed it anyway. So all these correlations in bold are significant. They're not high correlations, but they're significant. And these slopes, wherever a theoretical slope is shown here, it's within the 95% confidence limits of the data. So actually these are somewhat different, but still within 95% confidence. I didn't tell you what those limits are, but it's within it. Here there's no theoretical slope shown, and that's because PI theory doesn't tell you what the result should be for the MDR PI, because those storms didn't go in the MDR. You cannot compare the actual intensity of a storm to the potential intensity somewhere else. So, yes, Professor Starr.
Last year.
Yeah.
Can you explain the previous slide again?
Yes. This is just a summary of statistics from plots like this. So each year I have a potential intensity and an actual intensity for all this average for all the storms in that year.
Yes.
Right? So this is a scatter plot of those two things. PI, which is each point is 1 year average. So it might be an average.
But that's anomaly minus mean.
Yes, thank you.
Anomaly
Correct. Thank you very much. I take out the mean and I detrend.
Okay.
Sorry about that. I was not
No,
clear.
I understand.
Yeah, I wasn't clear. Okay, yeah, good point. And the variability you see is not that much, 10-20% of the mean. It's normalized by the mean. Thank you. Is it normalized by the mean or? Yes, normalized by the mean, not the standard deviation.
So the previous one is the mean per second. It's not.
That's right. That's right. This might be detrended, but I did not take the mean. So you're right. Before I do the scatter plot, I subtract the mean and divide by the mean.
Anomaly normalized
By the mean. Yes, thank you. So you see, it's another thing you see is it's 10-20% is the variation, not that big.
So you have correlation. You have correlation data. And why do you think you expect this from theoretical theory?
The theory does not tell you what the correlation should be, but you want to know what it is anyway, because if you want to use the theory, we're testing how useful is the theory. If there's no correlation, the theory is
We
useless.
like to see the certain correlation.
If there is a correlation, it tells you the theory will predict some of the variance, right? If there's no correlation, the theory doesn't help you. It might be right, but maybe there's some variability. The noise is so much you cannot see it. And so there is a significant correlation, but not large. Of course, if you were using the data if you were using the theory to predict decadal changes, you might get more significance because you beat down the noise when you sample over 10 years. Each one is an average for 1 year, so there might only be 5 or 10 storms in a year. So the sampling noise by itself is very large because you're trying to sample uniform distribution, but only 5 or 10 storms is not enough maybe to reconstruct that distribution well. Is that answering that? Yeah. Okay. So basically it agrees with the theory, but there's big noise and the correlation is low. That's almost everything I have on this result. This is the conclusion, and then I will show the next part of the talk, which hopefully I can do more quickly. So we used interannual variability to test this prediction, that the PI controls the maximum intensity of actual storms. Basically, it's saying that the thermodynamics, the theory says the thermodynamics controls the storms. For example, there's no account of vertical shear here. I didn't talk about vertical shear. PI doesn't know about vertical shear. The interannual correlations are significant in all cases of interest, but not large. The regression slope is consistent with the theory within uncertainties. The uncertainties are pretty big, but within those uncertainties, which is coming from the data, not coming from the theory, theory works. The other thing, which is not something we set out to show, but it's an interesting result that came out, is that much of the potential intensity variation along the actual tracks is controlled by the track changes, not by the PI changes. So the storms move to a different place where the PI is different, and then so the tracks may shift. In the Western North Pacific, it happened east, there's an east-west shift. In the Atlantic also there's a shift. And that changes the intensity by itself, even if the rest of the climate doesn't change. Okay, now I want to talk about something else. The Genesis Potential Index. This is just a picture of it, but I'll keep going to explain what it is. This Genesis Potential Index was developed by Carey Manuel. This is a conference abstract where they presented that. But it's based on an older idea by Gray. Gray originally came up with an index. I don't even know what the reference is, but you may have seen this before. The SST has to be greater than 26.5. The shear should be less than something. The Coriolis parameter should be, gets a few predictors, and he combines them into an index to show how likely is Genesis based on the environment. Okay? So this is just a new version of that. And you choose, there is some theory in it in the sense that which predictors you choose is based on what environmental factors we believe are important for Genesis. So we have some insight about that. The predictors are chosen a priori based on our insight, or based on Manuel or Gray's insight. But in the Manuel's index, one difference between Gray's is that we don't use any parameters tuned to the present climate. Gray's uses SST greater than 26.5 Celsius, but that threshold is just from the current climate. Under a warmer climate, probably the threshold for cyclone formation would be higher. And so you shouldn't use that threshold. It's been actually shown in GCM studies that threshold fails in global warming projections. So this one uses, instead of SST threshold, it uses potential intensity as one of the predictors. That's the main difference. Otherwise, it's similar to what Gray did. And then Emmanuel did a multiple regression combined with a little bit of subjective tuning that I can't tell you exactly how he did it, but I just show you the result of it, to obtain an index that reproduced the observed climatology of Genesis. It's supposed to get the seasonal cycle of the whole hemisphere, northern hemisphere, I believe, and also the spatial pattern in the climatology of Genesis. But it's just an empirical fitting procedure to relate those environmental parameters to their observed Genesis distribution. And the important point here is that there's no information, the tuning is just to the climatology. So interannual variability is not used to develop the index. So you can use interannual variability as a true, fair, independent test of the index. You compute the index, how it varies interannually, and compare it to how the storms vary interannually. And if it agrees, you say the index has passed the test. Okay? So this is the index itself. This is just the formula that Emmanuel came up with. Again, somewhat similar, qualitatively similar behavior to grades, but uses potential intensity instead of SST. So there's no SST here, but this potential intensity depends on the SST very strongly. So the SST is there implicitly. Eta is the absolute vorticity at 850 millibars. That includes the Coriolis parameter, of course, so it does know about the Coriolis parameter. H is relative humidity at 600 hectopascals. We believe mid-level humidity matters for Genesis. I think that's one of various parameters also. Potential intensity, I already talked about it, so that's the same potential intensity I showed before. We used the same calculation for an end-separator analysis there. And the shear is the vertical wind shear between 200 and 850 millibars. Just the normal way of computing wind shear. You might want to use some more sophisticated wind shear, but 200 minus 850 is normal in cyclone research. Okay, that's the index. This is what it looks like. This is plotting the color is the Genesis potential index. Don't worry what the units are. The units are arbitrary, but the pattern is what matters. This is for February, so southern hemisphere summer, and the dots are the observed Genesis location over some period of time. It's not the whole database because it would be too many points there. It's something like a few years or 10 years, just to show you that the points roughly line up with where the Genesis potential index is high. But it has to do that because the index was tuned to get that agreement. So it's not a result, it's just showing the fit. Okay? This is the same for September. Again, it captures the Genesis regions, Western North Pacific, although this hot spot may not be agreeing with observations quite so much. Eastern North Pacific, Atlantic, although actually this region, main development region, is actually somewhat not so high. We don't know why, but so the index is not perfect. But it gets the regions qualitatively, captures them. That's just the fitting did that. This is a climatology for the whole hemisphere. So it's showing over the whole data record and the whole northern hemisphere and southern hemisphere the observed number of storms in the best track data set. And this is a Genesis index, so it should predict number of storms. Right? The previous thing was intensity, this is number. This is observed number, and this is Genesis potential index averaged over those basins. So it captures the seasonal cycle very well. Again, it was tuned to do this. So this is not any test, it's just showing the fit. Okay? But the fit is pretty good. So it just shows, somehow he does something to come up with these exponents, some fitting procedure, and that gives you, this is how good the agreement you can get from those exponents. Not perfect, but. This is starting to have some new information. This is the annual climatologies in each basin. So Southern Indian Ocean, North Indian, Western North Pacific, North Atlantic. Just a few basins here. And this bars is the observed average number of cyclones for each month, the annual cycle, and this is the Genesis potential. And it does quite a good job on these annual cycles. Even in the North Indian Ocean, where there are two peaks, it captures that. And to some extent, this is built into the tuning, but there's some independent information here because it's not tuned to each basin separately, it's tuned to the whole thing. Okay, but now let's get to what we really want to see, which is the interannual variability. So this is now not coming from the tuning. This is all independent new information. So this shows the anomalies. Susanna, who did these calculations, looked at the ENSO time series and defined some El Nino and La Nina events in the usual way. The Nino 3 index has to be above half a standard deviation or something, or below half a standard deviation from the mean. I don't remember exactly the criteria, but it doesn't matter. She comes up with some list of El Nino and La Nina events, and then produces composites, the Genesis potential index. So this is El Nino, this is La Nina, and they look very similar except with a minus sign, so it seems pretty linear. And you can see right away some features that we expect. For example, the Atlantic in El Nino, there's a suppression, a reduction in the Genesis potential index. So we know that in El Nino, the North Atlantic has fewer storms usually. So the index captures that qualitatively. The East Pacific is enhanced, which also should be. And in the Western North Pacific, it's blue here and red here, so there's a shift eastward, which you know is observed in El Nino events. And La Nina is the opposite. So this is the southern, this is comparing to the observations, just showing that this is the same thing. I take this one minus this one, and it's pretty linear, so it mostly just doubles this one. And that's sort of the total ENSO signal, El Nino minus La Nina, for northern summer, northern cyclone season. That's this field. And this is the observed genesis density. So you take the best track data, you draw little squares, and you count how many storms in each square, and you get a density. Pretty noisy because the record is not that long and the basin is big, but you can see some agreement. Red here, red there. This predicts more storms, and that's mostly observed. This predicts blue here, so fewer storms, mostly observed, although a lot of scatter. And then here you have blue here and red here, a shift eastward. It's a little cleaner if you look at the track density. Really, so the track density is the same thing as genesis density, but instead of only picking, these points are the first point each storm appears in the best track data set. This is all the points, which strictly you should not compare to genesis, but it gives a similar picture with less noise. Okay, so you can see a little bit better the suppression in the Atlantic, the enhancement in the East Pacific, the eastward and equatorward shift in the West Pacific, and even some suppression in the Bay of Bengal. This southern hemisphere you should ignore because there's basically no storms in the southern hemisphere at that time, so the anomalies don't mean anything. This is for the southern cyclone season, and you see a northward shift and a northward and eastward shift in the Australian region, and that's mostly evident in the observed track density. Blue here and red here, blue here and red here. So the storms are shifting equatorward. And actually one interesting corollary of that is that you think that in an El Nino, convection should be suppressed over Indonesia, which it is, but actually the chance of a cyclone is slightly higher in El Nino, and that's true, that's observed, although it's still very rare, but it can happen in an El Nino event. And similar, well, in the South Indian Ocean, it's a little bit hard to say if this agrees with this. Even the track density is pretty noisy, but I do think there's a tendency for an equatorward shift. The blue is mostly south here, and the red is north, although it's a little noisy. Maybe you can even say you see this blue here, but I don't know. So it seems to give a good result. Qualitatively, we claim from these results that the interannual variability in the genesis potential index does capture the qualitative features, at least the spatial structure, of the observed anomalies in genesis itself. So it's a success for the index.
So the reason you use the track to compare with the genesis from this because you don't have enough data from the genesis.
Right. I mean, we first compared to genesis. We knew that this is the right way to do it, and it looks kind of okay, but very noisy. So Susanna just did the track density, and it looks similar but cleaner. So we said, so we show that, but I cannot defend it well. There's no real reason to do that. So if you like this one better, look at that. So now, since it works, we can use the index as a tool to probe a little more deeply the mechanisms of the genesis changes, the cyclone number changes with ENSO. So what we do is, because we have this, I will go back a little bit. We have this formula with these weights, these exponents. So this tells me if the genesis index is good, then if I change the shear by some amount, it's 5 meters per second, this exponent combined with the variability in these other factors tells me how much that should change genesis, right? Similarly, if I have some change in relative vorticity or in the latitude of genesis with the track shift, this exponent compared to these other terms gives me some idea how much genesis should change. So I have a way to compare the influence of these different factors quantitatively on genesis, if I believe the index is good, which we have now some evidence for that. So what we do is, we compute a new GPI, where for 3 out of the 4 variables, we don't let it vary year to year. We just set it to the climatology and keep it the same every year. So we kill the variability in that factor. And then the 4th factor, we let it vary according to the data. Right? So that's like a new genesis potential index that depends only on shear, say, or only on relative vorticity. And we do that for each factor, for each of the 4 variables. Now, it's not completely clean because the index is not linear. It depends on powers of those things which are not 1. So you have 4 new GPIs, and if you add them together, you don't get exactly the total 1. But it still gives us some, it's not that, the fluctuations are not that large, the nonlinearities are not that powerful. So we think it gives us some idea what's going on. So this again I showed before. This is the August to October Genesis potential difference showing the shift in the Pacific, enhancement in the East Pacific, and the suppression in the Atlantic. And now this is, so you have to remember what that looks like. Okay. Now this is showing the contribution of each factor, although it's not exactly, again, not completely clean linear calculation, but it's our estimate of the contribution of each factor. So this is the humidity, vorticity, potential intensity, and vertical wind shear. So let's look at the Atlantic first. What we want to see is blue in the Atlantic. Which one, I don't ask, which one of those factors looks like the total for each basin? In the Atlantic, the blue is mostly evident in the vertical shear, especially along the coast here. But these other, there's a little bit of signal from these other, but not very much. So it suggests that in the Atlantic, it's the changes in shear, the increase in shear with an El Nino event, or the decrease La Nina, that is most responsible for the ENSO-induced changes in cyclones in the Atlantic. And that's what most people think anyway. So it's not really new, it's just some more quantitative support for that belief. Okay. In the Western North Pacific, some authors, including Bin Wong and Johnny Chan, have written that it's the enhancement in vorticity in the eastern part of the Western Pacific, the sort of getting near the Central Pacific, that explains the shift of Genesis eastward. As the monsoon trough extends, you get a more vorticity, and that explains Genesis. Well, this agrees, this supports that speculation, but again, it's a quantitative, semi-empirical, but at least a way of quantifying that. It also shows, interestingly, though, that there's the drying in the western part of the basin near Taiwan, northern Philippines, is also involved in this shift because you have an enhancement here in the east due to vorticity, but a suppression here seems to be due to humidity. Of course, it's reanalysis humidity data going into this, so maybe you might not trust it, but it suggests both these factors are responsible for the shift in the Western North Pacific. The potential intensity does not contribute. In fact, it has the wrong sign. It goes negative in El Nino, whereas the actual intensity increases. The actual number doesn't really change or increases again. The vertical wind shear has a big signal, but it doesn't look like the observed pattern. Right? We want to see a suppression here and enhancement here, and this has kind of a different structure. So we don't think the vertical wind shear is really controlling that shift very, very much. Although the wind shear, in addition to being important for the Atlantic, also seems to explain the enhancement with El Nino in the East Pacific. Although there's some contribution from potential intensity, vorticity actually goes the wrong way there. So in each different basin, the different factors contribute differently. There's no one answer which thing is more important, but we have a way now of parsing those results. In the southern hemisphere, this is the full GPI, ENSO anomaly in the Genesis potential, and these are the 4 factors, so we want to see which one looks most like this. And I think the vertical shear has the most resemblance, again, to this pattern. If you look very carefully at the latitude of the node line here is a little bit north of 20, and the node line here is in a similar place. The red and blue are in similar places, but it's a little more complicated. This blue also has a strong contribution from the relative humidity. You know, there's a drying around the northern Australia and the sea here in ENSO, and that tends to push the cyclones equatorward. And the absolute vorticity may play a role, too, in enhancement here. So this, the potential intensity does not seem to have too much influence. The color scale are the same on all these, by the way, so you can compare the magnitude by eye. So the southern hemisphere, the wind shear seems to me to be the most explaining a lot of the pattern, but the humidity and vorticity are also relevant. So actually, there is some consistency throughout the basins in that in many of them, the wind shear is dominant or playing at least a large role in the interannual variability, but with relative humidity and absolute vorticity also playing a role. In almost no basin does the potential intensity play a big role in interannual variability. Although we know it plays a big role in the climatological structure. If the PI is too low, you will never get any storms. But For the variability, it doesn't seem to be important, for the interannual variability. The trend might be something else. This is still just ENSO. So that's all the results I want to conclude now on that part, and actually from the whole talk. So we've shown that this Genesis potential index, which is empirical, but it is what it is. And I think we might get similar results if we used a different index. We just use Emmanuel's because we liked that one and we had it. We could have used Gray or some other one. It might be just as good. I'm not saying Emmanuel is the best for this purpose. Although I think Gray has a problem for climate change. But anyway, this Genesis potential index is the only one we looked at, and it does successfully predict at least the qualitative features of the ENSO variations in cyclone number in really all the basins where there's a signal. This is a fair test of the index because the index was not tuned to interannual variability at all. So given this success, we can decompose the index to get information about the role of the different factors in Genesis. And we found that vertical shear is important for the ENSO effect on cyclones in the North Atlantic and the Northeast Pacific. And the mid-level humidity and the low-level relative vorticity are important to the Genesis location shift that's observed in the Northwest Pacific. The Southern Hemisphere is a little more complicated, but again, the shear seems to most coherently explain the structure, but really all the factors except potential intensity are important. So that's everything I want to present. If you want to read about it, the papers are on my webpage, or we can discuss more after. But that's all I have to present today. So thank you for your attention.
Thank you very much for the very exciting presentations.
Thank you.
So questions? Ready?
The Genesis index is come from is fixed to the data line.
Sorry,
The Genesis index is I think is the best fit to the data line.
it's the best fit to the climatology. Yeah. So what Emmanuel did is, what he does is he takes, so how he does it is, he just first decide, this is I did not derive the index, Kerry did, but this is my understanding of what he did. And I think it's similar to how Gray did it back in the 70s when he derived his index. First you decide what variables you think are important. You have to do that from your own insight, right? And these are the four we came up with. But this goes, people believe these variables are important for at least since Gray's time. Okay. So you pick those variables, then you say, well, how do we know how much it depends on each variable? What's the relative importance? So for that, these points show the observed Genesis points for a few years in the Southern Hemisphere, right? This is in the Northern Hemisphere. This is not all of them. This is a few years. So you take all of them, take all the points, and from that you make a two-dimensional field. You make a density field, right? You know how many storms in each box. You have a density field, right? Then you do a multiple regression technique to come up with the best fit exponents. These factors are just normalizing. This is just normalization. It's a non-dimensional. It doesn't matter. What matters is these exponents. So you do a multiple regression technique to decide how best to fit some combination of these factors to the distribution of Genesis in the best track data. Okay? But the fitting is done to the whole data set at once, all the years together. So that's why I say the climatology. So it's fit to the spatial structure of the annual cycle. Then there's some subjective part, which is that fitting technique gives some exponents, which are not round numbers, but Kerry decided that, well, there's so much noise in the data, I should not take it. If the fitting gives me an exponent of 2.8, I'll just make it 3 because the uncertainty is bigger than that, so I just take a round number. Is that answering your question or no?
Yes, but when you feed the data, there is some irregularity or beauty, right?
There is interannual variability in the time series, but the fitting does not use that because it's just fitting. If I put down all the storms from the whole 50 years together, right? Use that to make a density field, right? And then the fitting is to capture the spatial structure of that. But that fitting does not know which year each storm happened in. It's all of it together, right? So when the fit is done, it knows the total distribution of genesis, but doesn't know anything about the time history of that. So when I test on the time history, that's what I mean by it's a fair test. It's looking at the fluctuations year to year. The fitting does not use that. Yeah. I answered everybody's question.
And what about I thought might be some subtlety about how you define the vertical shear. Well,
That's right.
Maybe Brian
Yeah.
Ken, he and Kelly is working on this, but I haven't heard about their results yet. But
No, it's true.
It's because some different part of the shear may give you a different impact on the genesis.
That's right.
And they're trying to address that. Have you thought about that yet?
We've thought about it enough to know it's an issue, like you said, but we didn't do anything more. I mean, Professor Wu's question is why do we use 850 minus 200? It may be that some other measure of the shear is important, and actually Kerry Manuel's student is looking at this, and it's true. I mean, there's 850 minus 200, 200 minus 850 is just something somebody did a long time ago, and then everybody keeps doing it, but there's nothing magic about it. And they've used other things like, you look at the vertical shear profile, the whole vertical profile of meridional and zonal wind. You can compute a variance, for example. That's some measure of the total amplitude of the shear at all the levels. Or you can make some other, the shear is some complete function, right, in height. You can make many metrics of that function, and some others might be better than 850 minus 200. The answer is no, we didn't do anything about it. I mean, once if they come up with an answer of what is the best measure of shear, then we can put that in instead of 200 minus 850. There's no claim, I mean, neither Emmanuel nor us make the claim that this index is the best possible